Although such problems are often 2 or even 3-dimensional, approximate solution can be obtained by assuming the one-dimensional heat transfer using thermal resistance network that we have already discussed. In last lecture, we discussed about when we are having a multiple slabs or walls in series, then the total resistance we have calculated is R1 plus R2 plus R3 plus R4, that is equal to R total, and Q equal to delta T upon R total we have gone through. Now you can see here our system is different in this particular figure. You can see here we have a parallel layers. So heat transfer happens in this direction, the positive X direction. We have a 3 different layer. This is my 1 layer, second layer, 3 layer, and 4 layer, like that. Right? So we have considered this particular slab. What will be the heat transfer in positive X direction through the material 1 who is having conductivity K1 and material 2 who is having conductivity K2. So just like your electrical system, instead of having a series connection, now we are having a parallel connection. So you can observe here that our left side of this slab, our temperature is known to us as T1, and same way right side our temperature is T2. So here is a T2, right side we are having a temperature T2. Now the resistance are connected, or walls are in a parallel system, not in series. So you can make an electrical system like that. This is the resistance 1. This is the resistance 1. 2. The total heat transfer happens in this wall is Q. Out of that, Q1 is passing from one wall, Q2 is passing from second wall, and total heat transfer Q will be a summation of Q1 plus Q2. Right? So this is what is mentioned over here. Total heat transfer Q dot is Q1 dot plus Q2 dot. Now we apply the electrical analogy that Q1 dot is T1 minus T2, means delta T upon resistance of one material. Second is T1 minus T2, temperature difference is same, left and right. So T1 minus T2, but resistance here is R2. You can take T1 minus T2 common, then your equation comes to T1 minus T2 in bracket 1 upon R1 plus 1 upon R2. And that is equal to Q dot T1 minus T2 upon R total. So you can see here when we are having a parallel system, my R total, the R total will be 1 upon R1 plus 1 upon R2. Sorry, 1 upon R total will be equal to 1 upon R1 plus 1 upon R2. So R total will be equal to R1 into R2 divided by R1 plus R2. This is what the difference, same like your electrical system. If your resistors are in series, you can do the same. Like that. So this is what in parallel system. Now you see this particular example where you can see here the materials are given this way. First is insulation, this is insulation. Now heat excitation, 3 different materials. One is one whose conductivity is given. Second conductivity is K2. Third is you can see of K1 and K2, they are in parallel. So these 2 plates are parallel. You can calculate the distance of these 2 parallel plates. Then third plate is in series with combined of 1, 2 and this. Right? So if we make an electrical circuit like here we are having a T1 temperature, outside is T infinity as it is given here. So it is a T infinity temperature here. Now resistance 1. So Q dot will be split into Q1 and Q2. They are in parallel, plus third resistance which is in series with combined effect of R1 and R2, and then convection resistance is taken here. So now you can understand Q dot equal to T1 minus T infinity, temperature difference left and right side, divided by R total, where R total will be equal to what? Resistance of R12, means combined effect of resistance material 1 and material 2, plus S3 is in series, so R3, and fourth is R convection, where S1 and 2 are in a parallel. So as we have seen here, That R total, if they are in parallel, will be equal to R1 R2 divided by R1 plus R2. So that is what written over here. Resistance offered by a combined layer of 1 and 2 will be R1 R2 divided by R1 plus R2. Then R3 is same as resistance offered by third layer and convection. So R1 will be L1 upon K1A1, R2 will be L2 K2A2, R3 will be L3 K3A3, and R convection will be 1 upon H3. Once your all values are known to you, you can put into here, you will get R total. Once R total is known to you, you can put here. When delta T is known to you, you will get heat transfer. We will understand this parallel and series connection through one example, and which is a common example which you can correlate with your household application. That if we are using a heater in a winter season or AC in a summer season, there will be a heat transfer from windows, walls, doors, etc. So we have taken an example that what amount of heat will be transferred through a window if you are having a glass window. So data I am reading here is 3-meter high, 5-meter wide wall consists of 16 centimeter into 22 centimeter cross section horizontal brick whose conductivity is given, separated by a 3-meter brick thick layer of conductivity is given. There are also 2 centimeter thick plaster layers on each side of the brick and 3 centimeter thick rigid foam and whose conductivity is given. On the inner side of the wall, as shown in figure, I will show the figure, the indoor and outdoor temperatures are mentioned. Indoor temperature is 20 degrees Celsius you want to maintain. Outside is cold, which is minus 10 degrees Celsius, and the convection heat transfer coefficient of inner and outer side H1 and H2 are given respectively. Assuming one-dimensional heat transfer and disregarding the radiation, determine the rate of heat transfer through the wall. This is what the data is given. You are having a layer of different materials. First material is a foam whose thickness is given 3 centimeters. Second layer is a plaster layer. This layer is a plaster layer whose thickness is 2 and conductivity is mentioned. Then you are having a brick layer. So this is your brick whose conductivity is also given and its thickness is 16 centimeters. Then again a plaster layer and whose thickness is 2. And our task is to calculate the heat transfer. The all values are given. Conductive heat transfer coefficient H1 is given inside. Conductive heat transfer coefficient H2 is given to here. Room side your temperature is given 20 degree. Outside temperature is given minus 10 degrees Celsius, and we have to calculate this. So let us convert this actual wall system into resistance system, thermal resistance system. So temperature which is known to us T infinity 1. Ri is resistance offered by this particular wall, internal resistance. Then resistance offered by this layer of plaster, that is R1. Resistance offered by R2. Sorry, I mentioned Ri is convection heat transfer resistance. This is convection. R1 is this. R2 is this plaster. Now R3 we are having 3 different layers. You can say here one plaster layer, second brick layer, and third is again plaster layer. So this is 1, this is 2, and this is 3. They are in parallel. So R3, R4, and R5 are in a parallel system. Then R6 is again resistance of plaster, and RO is convection resistance over here. We have to calculate R1, Ri, R1, R2, R3, R4, R5, R6, RO, and then temperatures are given. We can solve it. So let us understand this. Solution is the composition of the composite wall is given. The rate of heat transfer through the wall is to be determined. Means our task is to calculate Q dot. What assumptions we are making? Heat transfer is steady since there is no indication of change in time. Heat transfer can be approximated as one-dimensional. So we will take X direction, positive X direction only. The thermal conductivity are constant, means conductivity which are given of foam, plaster, brick will remain constant. And heat transfer by radiation is negligible. So what we will consider is heat transfer by conduction and heat transfer by convection. So this is what your convection heat transfer resistance left side, convection heat transfer resistance right side, and remaining R1 to R6 are conduction resistance. The properties which are given, the properties, the thermal conductivities are given to be K equal to 0.072 for brick, 0.22 for plaster, and K 0.026 for rigid form. So form material conductivity is least or minimum, you can call it. Then you are having a layer of plaster whose conductivity is approximately 10 times greater than the conductivity of foam. That is, instead of 0.02, you are having 0.22. And last is a brick whose conductivity is highest among these three. Analysis. There is a pattern in the construction of this wall that it repeats itself every 15 centimeter distance in a vertical layer. So you can see here the wall, this 22 centimeter is the height of brick, 1.5 centimeter is thickness of plaster, and this is thickness. So it will be a 25 centimeter. Same will be here, 25 centimeter. Same will be here. So it is mentioned that the pattern is repeated in every 25 centimeter in vertical direction. There is no variation in horizontal direction. In horizontal direction, it is uniform. There is no change. Therefore, we consider a 1 meter deep and 0.25 meter high portion of the wall, since it is representative of the entire wall. So we will consider this thickness is 1 meter and height as it is given 25 centimeter, we will convert into meter, so 0.25 meter, and we will do a calculation. Assuming any cross section of the wall.
Hello, sir. Hello.
Yes.
સર અમારા હમણાં ડોમનો લેક્ચર પણ છે પોણા બારે. સરે હમણાં મેસેજ કરેલો છે ટીમ્સમાં. એકચ્યુઅલી ખબર નહીં પડતી ટાઈમ ટેબલ કયું છે.
Let me see. 1 minute. Let me check. If you have okay, today's lecture we were about to start at 9:15. Okay, so I am stopping here the lecture. Yes, you are having. I will send you the latest timetable, whole
Okay,
fifth
sir.
semester timetable. So you refer that latest timetable. Today we are stopping here, right?
Okay, sir.
So we'll continue with this numerical next time. Already data is given to you, and we will continue this one. So we stop here. You can